Alrighty, so in this video we're going to talk about half-lives. I'm going to change this to half-life here because that's not the name of this thing, half-lives. Okay, so in half-lives, we talk about radioactive decay, but it's not the mechanics of it, it's the rate of radioactive decay. How fast does it happen? That's the idea that half-lives gets at. And so let's get into this. Remember, radioactive decay is basically when you have some atom, in this case an atom named Atom, very conveniently, has its smiley face and it's stable, but then if it gets bigger, has more neutrons in it, then it's unstable, it's unsettled, and it wants to barf a few neutrons out, or protons, or electrons, or whatever of the decay, whichever of the decays we went over in the last video. And then when it barfs it out, it spits out energy as well. And then we have here a happy, stable atom once again. And so, what is a half-life then? A half-life, so this is just what happens for one atom. This is just one atom. Okay, number one atom. What about if you have a big clump of, let's say, uranium, okay, or commonly called yellow cake? If you have a bunch of uranium, how much of it is a lot of these radioactive elements naturally are decaying over time, and you don't necessarily want to be close to them because they can be at toxic levels, and they're just always decaying all the time. And so, at what rate do they decay? Well, that's exactly what we go over here. So, imagine you have this big purple clump of uranium-212. Okay? Now, you have this big purple clump, and let's say after, do I mention here? After 8.5 hours, okay, half of this uranium-212 is going to decay into some other element. And then you're only going to be left with this purple clump of uranium-212. 50% of it, of the original 100% here. Okay? Then if you're left with this 50% of uranium-212, you wait another 8.5 hours, and half of this gets decayed into this little clump of uranium-212. And you're left with 25% of the original 100%. You're left with this kind of corner over here. You're left with it down here. And then if you wait another 8.5 hours, let's just maybe continue, another 8.5 hours, then half of this uranium-212 will decay into thorium or whatever the case may be. And then you're going to be left with what's percentage of that when you have 25%? It's 12.5% of the original 100%. And then you're left with here with this uranium-212. Uranium-212. Okay? So each of the, after the same amount of time, 8.5 hours, it could undergo alpha decay, beta decay, gamma decay. Regardless of the decay, half of it will be gone after 8.5 hours for some reason. Then half of this will be gone, of the half of the 50%. Then half of the 25% after another 8.5 hours. Then after another 8.5 hours after this, then it's going to be left with 6.25% of the original 100, and so on and so forth. And that is what we call a half-life. A half-life is the amount of time, in this case 8.5 hours, the amount of time it takes for half of your radioactive material to decay. Okay? And we can actually graph this, and it creates a nice, clean exponential graph. So here we have at time 0, where time is years on the x-axis, and here, let me change the laser here. Time in the x-axis is years in this case, and in the y-axis it's the percentage of radioactive material. And so at time 0, at the very start, you have all of it, 100%. But then after one half-life, in this case it looks like it's carbon-14's half-life is, let's say it's 5,000 years. I don't think it's that, but let's say it's 5,000 years. Then after 5,000 years, you have half of this 100%. Okay? Then, after another 5,000 years, so a total of 10,000 years, you're left with half of that half, which is 25% right here. After another 5,000 years, you have that 25%, and you're left with that here. And then after another 5 years, half of that 12.5 gets decayed, and you're left with 6.25 of that original 100%. And so it creates this nice, clean exponential curve that gets closer and closer to zero until realistically every single atom is decayed. So you will have a problem similar to this, like uranium-212 has a half-life of 8.5 hours. 6.25%. You have 6.25% of uranium left. How much time has passed? We have to say, okay, in order to go from 100% to 50%, that's one half-life, so that's 8.5 hours. Then 50 to 25%, that's another 8.5 hours. So that's 17 hours so far. Then 25, another half-life is 12.5 hours. 12.5%, which is another 8.5 hours. And then half of 12.5 is finally 6.25%, which is how much you have left of it. That's another 8.5 hours. So that's 1, 2, 3, 4 half-lives pass by. So 4 times 8.5 is, 4 times 8 is 32. 4 times a half is 2. So 32 plus 2 is 34 years. Hours. 34 hours have passed. And so this is convenient because then we can do things like carbon dating. We can say like, okay, this body that was washed up in the river of some person has this much percentage of carbon-14 that they're supposed to have in their body. So how much time has passed? This many hours. Okay, so I put time of death as 3 days ago, which would be Friday night or Saturday morning or something like that. And then forensic scientists can provide approximate times of death with this type of radioactive decay knowledge and their tools that are created around it. Another typical question you might get is, you have 40 grams of plutonium-244. After 75 hours, you have 5 grams left. What is the half-life? Okay, and I think this one is missing some. I think it could be worded a little bit better, but essentially you just keep halving the grams. Okay, you have originally 40 grams. Half of that is 20. Half of that is 10. Half of that is 5. So 3 half-lives have passed in order to get to this 5 grams starting from 40. And if 75 hours total have passed, and you know that 3 half-lives have passed as well, then you do 75 divided by 3, and you'll get 25. 25. And then you'll know that 1 half-life is 25 hours. So you'll do things like that. That happens in research. And so practice these problems in class, and if you have any questions, we are here to help you.